Assalamualaikum and a very good morning everyone in Malaysia. Good afternoon to audience in New Zealand. My name is Ainizura Abdul Kadir and I will be the host for today's DLS session. Welcome to Faculty of Engineering Distinguished Lecture Series, UTM. And we are happy to have our distinguished speaker, Professor Xu, all the way from University of Auckland, New Zealand. So basically how I met Professor Xu, he's my former PhD supervisor back in 2010. And since then, we've been to several conferences together. Even School of Mechanical Engineering appointed him as our external examiner for master's program, Advanced Manufacturing Technology. And also, he's been given a colloquium session to our undergraduate, postgraduate students back then in 2013. So he's quite familiar to mechanical engineering, especially manufacturing department. And we are happy to have him again after 7 years in this DLS program. He's an expert in smart manufacturing and also cloud manufacturing. So without further ado, I would like to pass to our Dean, Professor Dr. Rafiq, to brief a little bit of bio regarding our distinguished speaker, Professor Xu. Over to you, Prof.
Thank you, Dr. Aini Zura, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh, and welcome everyone to our 70th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq, and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Xun Xu from University of Auckland, New Zealand. A bit about our distinguished speaker today. Professor Xun Xu is Chair of Manufacturing at the Department of Mechanical Engineering, the University of Auckland, New Zealand. He joined the department after completing a PhD from the University of Manchester, then UMIST, UK in 1996. He has been working in the field of intelligent manufacturing solutions for some 30 years. Dr. Xu is an internationally recognized expert in smart manufacturing systems, cloud-based manufacturing, and IoT-enabled manufacturing. He serves as an associate editor and member of Editorial Board of a number of international journals and has published over 350 research papers. Dr. Xu is the founding director of the University of Auckland Innovative Manufacturing and Materials Program, which draws expertise and experts from the Faculties of Engineering, Business, and Science of the university. He is the director of Lab for Industrie 4.0 Smart Manufacturing Systems, LISMS, the only laboratory for Industrie 4.0 in New Zealand. His current research focus is around the Industry 4.0 technologies, for example, smart factories, digital twins, cloud manufacturing, augmented reality, virtual reality for manufacturing, big industrial data, and data analytics. Dr. Xu is the Fellow of American Society for Mechanical Engineers, ASME, and Engineering New Zealand. In 2020, he is named among the 20 most influential professors in smart manufacturing by the Society of Manufacturing Engineers, SME. So that is a brief biography of our distinguished speaker today. Here now is Professor Xun Xu from University of Auckland, New Zealand, with his talk entitled Digital Twins in Industry 4.0. Professor Xun Xu, over to you.
Thank you, Professor Rafiq. Thank you, Ani. Thank you, everybody, for taking time to listen to my talk. For those who know what I've been doing, this talk will be a little bit different. In particular, different from what I used to do in the past 10 or 20 years. Partially because manufacturing is a fast changing field. Today, I will be talking about a new revolution of manufacturing industry, which has been coined by the German scientists and German government. It's called Industry 4.0. The topic is very big, but I choose to pick one of the key concepts in this area in Industry 4.0. So that is the digital twin concept. So focus on this, and itself is also a very big topic. And I just finished one of the postgraduate courses I run, and I gave my students a topic to work on this. So I had a couple of assignments on this already. So it's digital twin is already a big concept. But I hope my talk will give you some idea about the concept of Industry 4 and digital twin technologies. So the talk will start with a very brief introduction about digitalization and Industry 4. Then I move on to this concept of cyber physical system, which is a key concept under Industry 4. And of course, digital twin as well. And being the key topic of today's talk, I'll talk about the definitions and applications, models, and the twinning methods for digital twin. And believe it or not, there's already international standards for digital twin framework in the space. I mean, the concept is relatively new, but already, and the ISO committee is already working on a digital twin concept. The message I just got yesterday is that the draft standards has been approved and is going into the second phase. The actual international standards hopefully will come to life before the end of next year, 2021. So I'll talk about some of the commercially available digital twin tools, and you probably have come across some of them, but they, to some extent, are subset of the concept we talk about. We will talk about it about digital twins, so they're not fully fledged digital twin tools, in my view. And I'll talk about some of the user cases, some of the demonstrative cases. These are the cases that we have developed in the laboratory in the past maybe 4 or 5 years. So it's quite recent research work. So digital twin is the topic. So the word is digitalization. Well, when we talk about digitalization, it's probably not foreign to many people here, because we know this digitalization of economic and social processes already. We have these immaterial information-based processes being digitalized in the past, and so we still have it at the moment. Things like financing, banking, publishing, music as well, and other communication methods. But the key thing is to think about digitalizing not just immaterial stuff, but physical systems. So how do we do that? So this actually started in 2000. In year 2000, this is looking at how to use internet technologies to really provide a digital representation of a physical system, and for that to be seamlessly integrated with the hardware systems. So that's why we have this concept of cyber physical systems. You have a cyber plus physical, and that they join together to form a system. So it's a bit different from the first wave of digitalization. I thought I should show this diagram here. I think those who are interested in Industry 4.0 would have already seen this, maybe not once, not twice, many times. So here, the diagram shows the three industrial revolutions already happened before, and what we are experiencing at the moment is the fourth industrial revolution. You can see here the key words is cyber physical systems. So this is the diagram that published by German government, and this is the key concept of Industry 4.0. And the other documents actually shows the components of Industry 4 a few years later, which basically tells an ecosystem of Industry 4 and what we think Industry 4.0 should consist of. Well, I'm not going to go into the details of lots of this in this diagram, but perhaps draw your attention to the top of this diagram. You can see there's a physical aspect of manufacturing, and then there's a cyber or digital aspect of manufacturing, and they actually um, um, representing the same thing. So the cyber counterpart represents the physical counterpart. So that's the concept of cyber physical system. We have virtual representation of the physical systems, and they are combined to serve the purpose. So how do we define this cyber physical system, or CPS in short? Well, basically it is the marriage between the virtual and the digital world with the real world, real physical world. So this digital world will be called cyber twin or digital twin. So different people have used different terms. I think from now on we'll be using the term digital twin. Well, it represents a brand new scenario for manufacturing in the sense that everything is completely connected, but also with intelligence embedded in different nodes. So we are talking about not just a simple machine-to-machine communications. We're talking about semantic communications, meaning machines understand each other, not just at the syntax level, but semantic level as well. So just like two people communicating and talking to each other, they understand what they're saying, not just understand based on the format. So that actually signaling a brand new system. These are the close embedded systems, or the system that can actually self-monitoring, monitor and self-heal, and promote proactive communications with other machines and operators. When CPS used for manufacturing, and there's a more focused term, which is cyber physical production systems. So it's CPPS. Now, this may sound a little bit abstract, but I thought this is a diagram that explains things quite well here. I got it from this online magazine, Design World, published in 2015. This is basically showing the difference between cyber physical system and IoT. So we all know IoT in this case. If we have the equipment in the shop floor, different machine tools, for example, and they can be connected. So they're connected, and then they can be connected to the internet, or what could be an intranet as well. And that forms an IoT system. But what we're talking about here is we want to develop a cyber twin or digital twin of each one of these systems. And when we combine them together, we make them as one entity, so that will form a CPS. And so the communication between these systems are no longer between the systems themselves, I mean the physical systems. They actually communicate through their cyber twins or digital twins. And so that this kind of communication is far more powerful, and it can communicate not only data relating to the hardware, but also data that are processed and analyzed in the digital twin level. So this is far more powerful setting, if you like, for all manufacturing equipment. So we are talking about perhaps giving the equipment in the factory a brain which can think for themselves. So it becomes more a complete system, if you like. So it's a very exciting time that we are in now. I think technologies that have been developed for other purposes uh, can now be used for this concept as well. So we're looking at a matured scenario, both from the industry demands point of view, but also from the technology readiness point of view. Now, if we try to define this term industry, a digital twin concept, there are just literally perhaps, if not hundreds, at least tens of 20s, more than 20 different definitions people have been using, I've come across. But I want to give three of them, which represent perhaps the journey of the concept started roughly 10 years ago. So really it's a very new concept that started by NASA trying to develop a digital model with multiple physics and multiple scale and simulation tools to simulate their systems on fleet and look at their historical data and incorporating some sensors and try to mirror the life of its flying twin. So it's really looking at flying objects, um, aircraft and the like. So the key thing is still at that time is for simulation purpose. Then in 2016, this concept was introduced and is talking about digital twin being a virtual substitute of real-world objects consisting of virtual representations and communication capabilities, making up smart objects acting as intelligent nodes. So the key words are here intelligent nodes, but also they are provisioned in the internet as a service or as a thing, which in this case could be a CPS. And around the same time, and another definition is given by German colleague Kraft, is basically combining these two, but moving a step forward into incorporating sensor information, inputs data to mirror and predict activities and performance. So the term predict is important because that implies that there will be some analysis going on, some decision making going on in the twins, so that will affect the twins the other way around. So you're getting data from the physical twins, and you do some analysis and make some decisions, and hopefully that decision will inform the physical counterparts in terms of what actions to take. So we're really looking at these two twins coming together as a coherent entity. There are many examples of digital twins, and if you're talking about digital twins for smart manufacturing, we can have a digital twin for products. So anything that flows and move around in the factory as a product, we can develop digital twins. That twin will represent the product, but also will represent other metadata um, to go with the products, and in terms of the quality, the design specifications, and the processes being performed on that. Manufacturing assets, of course, machine tools and robots and assembly workstations. So it's possible to develop twins for these assets. And clearly, there are people in the factory, and typically, so there's a talk about developing digital twins for people, operators, and that makes some sense. And then digital twin of networks and others. Grievy is one of the early researchers developed this twin models, digital twin models. So he's talking about three dimensions of a digital twin. There's a physical entity, there's a virtual entity, virtual model of it, and there's connections So I've dimmed out the physical entity because if you're talking about digital twin, you're really assuming that the physical entity is the one that you're trying to develop for. So it's not part of the virtual model. It shouldn't be the part of the virtual model, although they have a close connections. And the key characteristics of this is really looking at how to bring them together. So there's an interaction between the physical counterparts and the virtual model of it. So that communication interaction is really important. So the virtual model contains a physical digital model of that. So that could be a geometrical model. So it could be a CAD model, for example. But it has to be more than that. And there's a physical properties as well. So there will be multi-physics as we talk about it built into this model. And it will be able to model the behavior of the equipment as well. So it's really comprehensive and very powerful digital model, if you like. And this model is often known as information model. Um, the the virtual model should also have the ability to be coupled with physical counterparts for virtual and real world synchronizations. So that's also very important aspect of that. So this diagram shows what we mean by uh, digital twins in the cyber physical system. So we have in the physical world, for example, the products that we make in the factory and the machines that we use to make the product. So these are the physical entities. Now notice that I don't have people here, and I did talk about people can be one of the entities to be developed for digital twins. But just looking at the products and machines, and we can have a digital twin for the products and machines. And in this case, these are perhaps primarily the geometrical and the physical models of it. But I think what we need to also have in the digital twin space are the capability models in terms of what they do, the functions of these products and machines, but also a knowledge base that we built for running these machines or for using the product and for making the product. And what's also necessary is some analytics tools in the twins so we can use it to optimize the process to do some analysis and decision making and so that we can actually have information and data and instructions flow back into the physical world. So that's why I have this double arrowheads there connecting the digital twins with the physical world. So it's a concept that goes beyond just the model itself. Now, the communication is important. The training method is important. In other words, the communication between the physical systems, the sensor data goes into the twin, and the data from the twin back to the physical worlds. So that's important. And so if we have a just quick look at the twinning mechanisms that we normally have, that there are quite a few. And you can use some industrial field bus network. So we won't go into the details of this. You could use Ethernet-based industrial network protocols. And then, of course, increasingly, industries are using wireless networks. Different type of protocols have been developed by IEEE. And there are others as well, MQTT and OPCOA and MET Connect. Now, so these are the twinning methods, and we still developing other methods. Some of them will be useful for certain type of systems, and others will be for others. So I mentioned about the international standard for digital twin. This is a very interesting phenomenon, I think, something that is new that we're already seeing the international standard being developed. So I thought it would be useful to mention about this ISO standard, but only very briefly. But before we do that, maybe it would be a good idea to look at the international standards supporting the processes from design, planning, inspection, manufacturing, the entire life cycle. Looking at the standards started from 1980s all the way to present time. There are a number of standards developed to support this. Of particular significance are these ones. There's a ISO 14649, and Ani was working on her PhD using this standard. So this is the step standard for NC machining. Then around 2014, there's a smart manufacturing standards coming out. There is a AP242, which is a brand new step standard that is going to replace or is already replacing AP203 and the AP214. So this is the future of CAD data exchange. And then, of course, there's AB238, which is another step in C standards. And what we are seeing at the moment is a brand new ISO standard being developed, which is the digital twins for manufacturing. So it's ISO 23247. So I think you can Google this and you will find some information about the standard. So it's still being worked on. There's draft available for industry to review. So the standard itself, the name of the standard is called Automation Systems and Integration and Digital Twin Framework for Manufacturing. So it's really for manufacturing only, but it could be used for other processes. So what it claims is the twin framework that's been developed and may exist across the entire life cycle. That's very important. It's representing a full life cycle, and it leverages three different aspects. There's a virtual environment, which is the virtual physics and external data as well that coming into the model, and the computational tools that we use to do different type of analysis and optimization, and the physical environments in a sense that the data may come from different physical entities, so that will come into digital twin for analysis and data processing. So that's the international standards. There's a diagram in the draft standards, which I think is really nice diagram to explain how this digital twin framework should function. So we have down at the bottom here what the standard called observable manufacturing entities or elements. So these are the things that we can feel and see them. So the people there and equipment, material, process, facilities, and everything else. So then we can actually develop twins for each one of these. And between the twins and the physical entity, we need to have the data collection mechanisms and device control mechanisms. So this is DC-DC protocols we need to have. So control meaning we hope that one day the twins can control the hardware. The data collection is more from the physical worlds to the digital world. So that's the twin space, but twin will be of no value if it cannot be used by different customers and users. So there's an application layer here, which is very important to really realize the full value of cyber physical system in this case. So hopefully it can do real-time control and offline analytics as well, because it does receive lots of data from the physical world. And they can do health check in terms of the machinery, whether it needs maintenance, or whether some machinery is giving problems in terms of not being able to maintain the accuracy, and predictive maintenance as well. If you monitor a system proactively, you will be able to predict things to happen, and you exercise your maintenance regime and properly. So I think this is a good diagram to really capture the digital twin concept for manufacturing, and also where it can be used. Application for digital twin for manufacturing, I'll talk about that. So it's basically just put them into words. It's real-time control, which is possible, and offline analytics, predictive maintenance, and health check. There's actually another diagram in that draft standards, and very similar. So we have physical and manufacturing. So these are the observable manufacturing elements, and the digital twin manufacturing framework. So the standard itself, ISO 23247, is about this part of the diagram. So it's developing this framework. So it doesn't have the very detailed protocols as we have for different APs in the STEP standards. But that will be, of course, and the following steps after this is published. So there's a data collection is important, device control layer as well. So you have a twin layer here, and then connecting to the users. So you can see that users are not directly connected to the physical elements. They are connected to the elements, the physical elements, through the digital representation. So that's the key concept of the cyber physical system. So that's the international standards. I did say that I'll talk about some commercial digital twin tools or software tools. So I'll just talk about maybe 4 of them very briefly, 1 slide each. The first one is from ANSYS. So those who do analysis using ANSYS will know some of their other products. So they claiming to be able to build a twin using their tools for predictive maintenance. So this is just leveraging their technical capabilities in ANSYS in terms of what it can do. So you can actually build the physical models using the tools there. So the models will be in a digital format, of course, and the model will be able to receive real-time data to power the system. And then you can do a validation process using some of the tools that they've developed, and of course deployment. Once you're happy, you can deploy that into industry. So that's a digital twin concept coming out of a typical CAE software, computer-aided analysis software. The other one is from Microsoft, Azure Digital Twins. Some of you perhaps would have come across this. So this is actually a platform tool for developing digital twins. So it has got this open modeling language. So it's developed a language for you to develop digital twins. So it's high-level tools, and I think it's good that there's some languages that are specifically for digital twin development. Some commercial systems are using the tools already. The third one is from Siebel. It's the one that is used to optimize the processes. Really trying to look at the production process using some artificial intelligence tools and to find out the root cause of some of the problems and the root cause to the problems, and the maintenance and predictive and alert as well. So it's very much a process digital twin, if you like. It's a process of manufacturing process. And Autodesk, they produce some design tools. For example, Inventor is the flagship products they're making. So digital twin is also in their minds. So they are leveraging other tools, other software tools, to actually build digital twins using the tools that originate from modeling geometry, basically. So again, this is an example of digital twin concept developed from a design perspective, or from a CAM perspective. So these are the 4 commercial digital twins. They're not quite ready to be used for manufacturing companies, and they cover a certain aspect of manufacturing. But I think we really need a more dedicated digital twin framework. So that's why the standards comes in handy. We hope before the end of next year we have this international standard formally published. The last thing is to just go through some of the demonstrative cases that we have developed, and so these are the research projects that are happening in the lab. So I want to talk about 3 cases that are developed in the laboratory down here. We talk about the digital twin of a custom products, in this case the bicycle. So we were looking at the product itself, how we can develop a digital twin for it. And the digital twin of machine tools, so these are the machines that we use to make products, and how do we develop digital twins for it. So if you have a digital twin developed, then the machine tools will become a cyber-physical machine tool, CPMT. And we have a quick look at retrofitting a old robot, a legacy robot. Anya will have memory of that robot, so we can make that robot able to communicate through the internet, and to eventually develop a digital twin for the robot. Right. So first up is this bicycle. Well, this is actually a poster from one of the students in the lab, Errol, and he's actually finishing his PhD. So without going into the details of this, it's a very busy diagram. My apologies for lots of information here. But if you look at the bicycle here, what we're saying is we're actually combining a virtual model. So this is part of the bicycle CAD model, can be combined with the physical model. So the virtual model is in CATIA, I think, or SolidWorks format. And then the physical model will have different sensors there mounted on the bicycle. So it gives information about the speed, pressure maybe, angular velocities, and everything else you may have in a bicycle. So we retrofitted bicycle with different sensors there. The sensor data will go into the digital model, and digital model will be driven by the actual data. So this is the process. So we sense that the actual physical model, then we acquire the data from the sensors. We map the sensor data to the digital model. In this case, it's just simply a CAD model. And now we can use the data to actually implement and augmented realities and other methods. Well, this is actually an example of augmented reality applications. You can see here, these are the data actually overlaid onto the actual bicycle. So if the bicycle is moving, you will be able to see the data changing accordingly. The second example is a machine tool. So the machine tool, if you develop a digital twin for that, so the twin plus the machine tool itself will form what we call cyber physical machine tools. Again, there's a quite busy diagram here and busy poster here. So the attention is on the physical device here, and we are developing a twin here. And the communications happens in between, of course. We use different protocols between the physical entity and the cyber twin. Notice that connecting to the cloud is through the twin itself, of course, and interface with the designer and the planner through the clouds, or it could be to the physical device directly. And the user interface, the HMI, is typically of the digital twin, because that can provide a very information-rich representation of the machine tools. And once you make some decisions, you will be able to come back and to implement decisions on the physical machines. So that's the diagram, and just a couple of more diagrams about this particular example. You can see here there's the desktop machine tools retrofitted with different sensors there. So we managed to stream this data into the twin to make decisions about manufacturing processes. And the data we're getting, for example, the utilization data, the axis position data, cutting forces, and cutting vibrations. So these are all real-time data as you do the machining process. Once you have the data, you can easily using technologies like augmented reality to visualize the data. So that's the actual physical setup. You can see here we've got the toolpath overlaid onto the actual video there, the actual picture there. You can also have the workpiece overlaid onto that, so you can actually see the information that you wouldn't be able to see because of the messy situation on the machine tools. The final example is this retrofitting system we've done. So this is really looking at retrofitting a cooker robot, which is fairly old, using a very simple wireless microprocessors, so that we can actually using protocols like MQTT to connect to the Azure platform. And the platform will running on the cloud, providing different functionalities. So this is actually very important for industry, that they have legacy systems. They do not want to throw them away. And how do you make a very old system to actually tell you the information you need to know? So this is a good example of retrofitting old systems for Industry 4 scenario. I think I've just tried to quickly go through these slides. I'll finish off with this final one here. Usually I'll present this to people who actually are considering doing research in this area, and so we welcome people to come into our laboratories to do research work. And there's also a virtual tour you can actually join. So if you scan this barcode, you will be able to come into our laboratory and enjoy a virtual tour of our laboratory. But I have to say that we've now moved out of this old laboratory. We're actually in a new building now. We're working on a new version of this virtual tour. You can also visit our website here down at the bottom. So with that, and I think I should conclude. And thank you for your attention. And I think we have some time for questions. I'll be happy to accommodate any questions.
Okay, thank you very much, Professor Xu, for that interesting and very informative lecture. It's tremendous to see how the technology actually grows from previously in the 90s, we just have IT. Then suddenly 2000, we start with the PhD work, ISO 14649. And then 5 years later, we talk about virtual manufacturing, cloud computing, comes to cloud manufacturing. And then later, recently, cyber physical machine, and then the IoT. And now you're talking about the digital twin. So it seems like the ISO are doing a very tremendous work to make the previous dreams of the IT people comes true in the area of manufacturing. So I'm happy if there's any question from the audience. I open for the Q&A. Yeah. Okay, from Nur Hayati Hussein, we have a question. In future, many manufacturers try to make more hybrid system in cyber physical equipment facilities instead of full integration system, which to reduce the space and data utilization. Any comment? Yes, Prof.
Right, I wasn't quite sure understand the question. And hybrid systems in cyber physical equipment instead of fully integrated systems. What do you really mean there? Hybrid systems,
Great.
meaning physical and then digital?
In
I,
hybrid.
yeah,
Yeah, probably the combination of both cyber as well as the actual physical. Uh, but then they want to fully integrate it into a virtual system, I guess.
yeah. I mean, to reduce the space and data utilization, um, I guess reduce the space maybe is less of an important thing to do. Not, but you don't want to reduce data utilization. You maybe want to increase data utilization. Well, I think um, if you look at the manufacturing industry, if you look at the equipment manufacturers, um, over the years, the early versions of machine tools, for example, they just are physical tools. There's a limited electronics in there, of course. And gradually we'll build into computing powers into the machine tools. So machine tools can do certain sensing tasks. Machine tools can actually make some decisions of their own. And now we have machine tools which can be readily connected to the internet or Ethernet. Um, so I think this electronic and software components of any equipment is increasing over the years. So that hardware aspect is reducing in terms of the value it adds into the entire system. So if you look at a system that has got hardware components and software components, I think that software components is increasing over the time and also adding value. And people buying things, perhaps looking at the software components instead of looking at the hardware appearance, how big the machine is, how fancy, how colorful the thing is. I think they're looking at the functionalities behind it. I think this is true for manufacturing, that things are being digitalized and things are being combined and having multiple functions.
Okay. Can we have another question? Next question.
I'm not sure whether I answered the question well. If I haven't, perhaps ask again in a different way.
Yeah, maybe can offline contact Prof through email.
Hmm.
Is there any more question from the audience? Maybe while waiting, okay, I have one general question related to the topic. Is there currently any challenges to adopt the technology, especially in the SMEs, small medium enterprise, mainly in the developing countries? Because it seems like it's an effort of big vendors, manufacturing vendors, instead of small medium enterprise companies. What do you
Yeah, I
think?
think that's a good question, Aini. Well, New Zealand is probably not much too different from Malaysia
Yeah.
or from other countries with primarily SMEs. Um, I think there are two things here. I think one is we need people at management level to recognize the potential of these technologies and to be on board with what we call digital transformation for manufacturing. The second thing is for small businesses, you probably want to start from small scale, baby steps, if you like, at the beginning.
Yep.
If you look at the business we have at the moment, and they're probably not industry 3.0, some of them maybe still industry 2.0. I don't know. So the efforts will be on developing some digital strategies for manufacturing companies first, and have some sort of roadmap, and then start small, start from basics, and start with some low-hanging fruits,
Yep.
so that you can have some revenue. You can have some cash flow coming in based on your project, but also showcasing and or can help convince the people in the factory that it is something that it will work.
Okay. Thank you very much, Professor Xu.
You're
Uh,
welcome.
All right, I think that will be the end of the session. I would like to thank Professor Xu for his time and also a very interesting lecture. Thank you to all audience for attending. Thank you, everyone. Hope to see you in another series.
Thank you, Dr.
Thank
Aini,
you.
for chairing the session. And thank you as well to our distinguished speaker today, Professor Xun Xu, for accepting our invitation to speak at our distinguished lecture series. To all of you, our audience watching this webinar, thank you for watching. Do stay tuned because we have many more interesting lectures for you. Until then, bye-bye for now. Bye-bye, everyone. Bye-bye.
Bye.
Thank you. Bye bye.